This one is 2.15, and this one there are some miners that are trapped 2000 meters below the surface. From here they make their way to the bottom of an abandoned shaft, so they are right now located here, and there's a hoist here through which we can drop a rope down, but the length of this rope is only 1990 meters. So basically, even if it reaches here, there is still that gap of 10 meters there, right? Now this rope is heavy, so each 30 centimeter of this rope is having a weight of 10 newtons, and the stiffness for that 30 centimeter is also given here. Now we need to figure out whether this rope can be used to bring these people up or not. So now there are two things that will happen with the rope here. So we are, let's say our target is for this rope to touch this line right here. So there is still this gap of 10 meters there, right? So how do we achieve this 10 meter gap so that these people can hold on to this rope? There are two factors there. One factor is that self weight, and this self weight is going to have some elongation in the rope. Okay. Second factor is, if the self weight is not sufficient, then maybe we can attach some extra weight while we drop this rope. Okay, so slowly when we are lowering this down, we attach a weight at the bottom so that that weight will also elongate this cable. Okay, now these two put together should be more than 10 meters so that they can come up. So let's look at the first case when only self weight is there. So if you look at this cable, let's say this is hanging in this manner here. Okay, so now at any cross section here, if I cut it right there and try to analyze the forces on it, there will be tension right here, which is T, and there will be this weight acting downwards. Now since this weight is per unit length there, so this weight is going to be only for this length right there, right? So how much is this weight? This weight can be written as 10 newtons is the weight for 30 centimeters. So this is the per unit length. Now how much length we have covered is this right here. Now from the free body we can see this tension is equals to weight, so this is the tension. Now next thing what we do is we go to this location and pick a small element which has a length dx there. So if I pull out that element here, I am assuming that it's having tension T on both sides. So the elongation in this small segment d delta can be written as T times dx, which is PL over EA, which is your Hooke's law. So PL over EA, we are trying to write that. So tension is the force, dx is the length of the element, elastic modulus E, and the cross section area A. And this problem, elastic modulus is not known, area is given to you. But there is this additional information which says a 30 centimeter length of this rope has a spring constant which is 2 into 10 power 6 Newton centimeter. So what does this mean? Let's draw one 30 centimeter long section there. So for this section, if you are pulling this by force P, the stiffness for this section, which is from this formula we can see is E over L, is given by 2 into 10 power 6 Newton per centimeter. Now what is the length of this section? This is 30. So L in this case is going to become 30. So this will give us EA value to be 60 into 10 power 6 newtons. So this is one constant that we can use in this relationship right here. Now this d delta that we have calculated is for this small dx element, right? So if you have to find out the total elongation, then we can do the integration of this delta from 0 to delta, and your x value there can be integrated for the total length of this wire, which is 1990 meters. So we can substitute the value of t here. The value of t is coming from this relationship. So 10 newtons divided by 30 centimeters dx 60 into 10 power 6 newtons there. So now if I do this calculation, your delta value from here comes only 1.1 meters. And how much we needed? We needed 10 meters at least. So definitely the self weight is not going to help us. So now if self weight is not helping and we have to reach this 10 meter, how much more we require? If we are interested in putting extra weight there, so let's say if we are putting extra weight W, we need from this 8.9 meters more so that it touches the ground, right? So now we can find out this W by comparing this 8.9 meter, which is your delta, equals to W times L over EA. Now L in this case is going to be the total length of the wire, so 8.9 meter times EA divided by L, which is 1990 meters, is going to give you the value of W there. Now what is the value of EA? We already have this value EA here. So if we solve your W in this case, it is 268.3 kilonewtons. So this is the extra weight that we need to hang at the bottom of the rope. Now what we need to see here is that when we are hanging this weight at the bottom here, and in addition to that there is that self weight present, is your wire strong enough to hold that weight and the self weight? Okay, so let's say if you do a rough calculation based on this W itself, you can check the value of stress, which is going to be W divided by the cross section area. In this case, cross section area, because the diameter is given, so it's going to be pi d square divided by 4. So if I substitute these numbers there, 268.3 kilonewton there, and pi, this is 2.5 centimeter square divided by 4. Now this number right here comes out very big, which is more than 500 megapascals. Okay, so this requires a material which is going to be very, very strong. So if you think in terms of your steel may be yielding somewhere around 300 to 400, and it may go to the failure at 400 to 500 megapascals. So this is definitely not a safe design. So we need to figure out another way to do this.